Previously, we have seen about the various configurations of field effect transistors as a common source, common drain and common gate, and with different biasing techniques. So let us shift to the FET amplifiers, where we are biasing the field effect transistors. So we have to see what is the need of biasing first. The concept where we were already discussed regarding the bipolar junction transistors. So whatever be the biasings we will be using for bipolar junction transistors, the same concept will be used for field effect transistors. And these biasing techniques used to maintain, to get a high outputs, and that can be possible when we maintain a constant operating point in the output characteristics. So whereas the operating point, it has been given in the active region of bipolar junction transistors, which maintains a constant operating point to get a high outputs. In the similar fashion, the output characteristics here in case of field effect transistors are transfer characteristics, where the operating point can be maintained stable for the transfer characteristics of a field effect transistors. So this operating point is nothing but a stable output current to that of the stable output voltage. As we have seen that, so the drain current ID is an output current for the case of field effect transistors, and the output voltage is VDS. So to maintain a stable values of ID and VDS of various values of transfer characteristics, so we can get a load line by adding all the operating points at different values of ID and VDS. We'll get a constant load line. So the concept what we have used in the BJT, same we are using here. Now here we will see how can we maintain a standard operating point in case of field effect transistors. Okay, so that can be analyzed by using DC analysis. By giving an DC input, we can analyze these circuits to get a stable operating point. So to get a stable operating point, so some of the initializations it has been made that, so this gate current IG will be equal to 0 and ID will be equal to IS. It is ID equal to IS, where the drain current will be equal to source current, and the third one, the drain current will be equal to IDSS into 1 minus VGS by VP whole square. So this it has been already proved in case of the 6th unit field effect transistors, where drain current it is, and IDSS is in a maximum current which is flowing through the device. Okay, so and VGS is a voltage between the gate and source, and VP is a pinch off voltage. So these are the approximations have been made to get in a stable operating point. So this operating point can be studied in 3 different biasing technologies. So as we have seen earlier, the fixed bias technology analysis and voltage variable biasing stage and self bias technique. So these are the 3 different techniques we are going to analyze now in case of field effect transistors with the following approximations. So let us first shift to the fixed bias technology technique, where in case of the fixed bias circuit, the same circuit I am using as we have analyzed in case of common source analysis. We have seen the fixed bias circuit. The same circuit I am using here to to analyze this circuit here, where the same everything is same here. It is in a N channel, as the arrow mark is towards the symbol here. It's in a gate, drain and source, and it is in a resistance connected towards the drain terminal, so the drain resistance, and the supply given here it is in a VDD, and the source here it is in a source terminal, and the gate terminal it has been given in a resistance is the gate resistance. And always to maintain the input circuit as a reverse bias, as it has a high input impedance, so it has been given as a reverse bias. So VGG is applied to the input of the case, and here VI is an input, and this commonly the C1 and C2 as a capacitors which are maintained over here. Okay, to amplify the signal, there we have used a C1 and C2 to get in a pure AC signal here. Now we are analyzing this circuit by using DC analysis. So to draw this simplified diagram, so this capacitors C1 and C2 will be open circuited, as we are analyzing this circuit with the DC bias. Means when the DC signal is given, so these two will be open circuited. As we know, the function of capacitor, it blocks DC and allows AC. So as analyzing is done by a DC bias, so this capacitors will be blocked off, in the sense it will be of open circuited. Then the simplified diagram can be drawn for the case of fixed bias in the simple diagram which has been given over here. So the same everything have drawn over here. So except here there will be no, these capacitors will not be considered here. It will be often an open circuited for the case of DC biases here. So it's in a simplified diagram which is drawn for this fixed bias technique here. So this can be analyzed. Now how can we maintain a stable operating point? It can be analyzed by simple concept here. First we have to draw in a simplified diagram of an actual diagram, then applying KVL to the input of the circuit and applying KVL to the output of the circuit, we can get the values of a constant ID value and constant VDS value. So that gives an operating point, that is nothing but Q point. So let us see how can we analyze that. So coming to the DC analysis here, first initially as I said now, applying KVL to the input of the circuit. Now it is an input of the circuit, it's an VGG which is given as an input here, and VGS is the voltage between the gate and source. It is the input voltage, so it is an output current ID and it is an output voltage VDS. Okay. Now see, by analyzing here, applying KVL to the input of the circuit, so the sum of these two voltages will be equal to 0. So now VGG plus VGS equal to 0. So which is given over here, VGS plus VGG equal to 0, then obviously VGS will be equal to minus VGG. Now as we know that, I have told that we have to approximate the following estimations. It has been given here, ID equal to IDSS 1 minus VGS by VP whole square. So it's a standard drain current flowing through the device during the operation of this FET. So that the same concept I have used here, the drain current is of the represented by the same expression here. Now applying KVL to the output of the circuit, see applying KVL, it's very easy for the output of the circuit, where VDD will be equal to sum of all these sources here. Now we can see here VDD is equal to ID RD plus VDS. It is a voltage across the drain and source. So this will be equal to the loop equation for the output of the circuit. You can see the equation here. So VDD will be equal to ID RD plus VDS. Same, VDD equal to ID RD plus VDS. Now, so as we want now VDS in the now output voltage here, so VDS will be equal to VDD minus ID RD. So this gives the final expressions for the output drain current as well as output drain source voltage here. The Q point finally for the fixed bias, it has been given by the equation here. So IDQ, it gives an operating point parameter. IDQ is equal to IDSS into 1 minus VGS by VP whole square. Similarly, VDSQ is equal to VDD minus IDQ is an operating point, once again the same, so RD. So these two values maintain a constant or a stable operating point. So this is how we can explain the technique of a fixed bias field effect transistor, the first type, where we can maintain a constant operating point. So here the operating point is nothing but IDQ and VDSQ, which was given by these following equations. Similarly, we'll see the other type of techniques. Next we'll see a second type of technique, so which is called a voltage variable biasing technique. So earlier we have seen about the fixed bias and verified there was any operating point where we can maintain a constant Q value. In similar fashion, we'll see the voltage variable bias. How can we maintain a constant operating point? So the circuit, it has a small modification in case of the earlier fixed bias, as we were using a gate resistance followed by a gate voltage VGG, whereas it has been replaced here. We won't use any voltage bias at the input of the circuit, where we'll be replacing it by a parallel resistance circuit. It's R1 and R2 to the input of the circuit, and remaining all the circuit will be same, and here we'll be making an extra element, that is a source resistance will be added parallel with the source capacitance. So it has been given already. I have told that in order to avoid the loading effect and it may affect the output voltage gain, so it has been arranged over in parallel with that of the source resistance. In a similar fashion, we can draw in a simplified diagram to analyze to get a constant operating point. See here, it has been given, it's in a constant voltage VG, it has been given here, where IG will be equal to 0, as it's no VGG it has been applied here. So that the same circuit it has been given, the rest of the circuit is almost same as that of the earlier circuit, as here this capacitors will be open circuited as we are analyzing this circuit by using the DC bias. So see, it's a VDS voltage is measured between the drain and source, and it has a separate, now we have a source resistance here. Then the current passing through the source resistance will be of a source current IS. So that voltage across that source resistance is given as VS here. So now we'll see the analysis of this circuit. Now the same have told, we have to apply the KVL to the input of the circuit. Then by applying KVL of the input circuit, see here, so we will get an here VG minus VGS minus VS we have. There are the three circuits which are coming over here, sir, because here's the voltage VS will be coming in the picture over here. So these are three types of voltages which are analyzed in the input of the circuit by applying the KVL here. So this will be equal to 0. Finally we will get the input voltage VGS will be equal to VG minus VS. I have told that as VS will be equal to the product of IS into RS. So it's the equation which is resulted by applying KVL to the input of the circuit. Next, from the output of the circuit, by just applying the KVL to the output of the circuit, see here VDD will be equal to, the current is ID and RD. VDD will be equal to IDRD plus VDS plus VS. So VDD will be equal to sum of all the sources present in the output of the circuit. The same I have drawn written over here. So VDD will be equal to sum of IDRD plus VDS, the voltage between the drain and source, and the voltage across the source resistance. So now this VDS, as we want the output voltage VDS, so VDS will be equal to VDD minus, taking this minus RD, and VS can be replaced once again as an VS is equal to IS RS. The same I have replaced here, VS will be equal to IS into RS. But taking the next step by taking ID as common here, so the RD plus RS. So this is the final value of an output voltage, and we know that the final value of output drain current ID is equal to IDSS into 1 minus VGS by VP whole square. It's on the same operating point we are using for this case, so that the Q point which is finally resulted as for the case of voltage variable bias, so IDQ is equal to IDSS into 1 minus VGS by VP whole square. The same, just the VDSQ is equal to same VDD minus IDQ into RD plus RS. So only the terms, the source resistance have come into existence extra compared to the earlier type of technique. So similar fashion we can analyze the circuit by the self bias. Next we'll see a second type of technique, so which is called a voltage variable biasing technique. So earlier we have seen about the fixed bias and verified there was any operating point where we can maintain a constant Q value. A similar fashion we'll see the voltage variable bias. How can we maintain a constant operating point? So the circuit, it has a small modification in case of the earlier fixed bias, as we were using a gate resistance followed by a gate voltage VGG, whereas it has been replaced here. We won't use any voltage bias at the input of the circuit, where we'll be replacing it by a parallel resistance circuit. It's R1 and R2 to the input of the circuit, and remaining all the circuit will be same, and here we'll be making an extra element, that is in a source resistance will be added parallel with the source capacitance. So it has been given, already I have told that in order to avoid the loading effect and it may affect the output voltage gain, so it has been arranged over in parallel with that of the source resistance. In a similar fashion we can draw a simplified diagram to analyze to get a constant operating point. See here it has been given, it's a constant voltage VG it has been given here, where IG will be equal to 0 as it's no VGG it has been applied here. So that the same circuit it has been given, the rest of the circuit is almost same as that of the earlier circuit, as here this capacitors will be open circuited as we are analyzing this circuit by using the DC bias. So see, it's a VDS voltage is measured between the drain and source, and it has a separate, now we have a source resistance here. Then the current passing through the source resistance will be of a source current IS. So that voltage across that source resistance is given as VS here. So now we'll see the analysis of this circuit. Now the same I have told, we have to apply the KVL to the input of the circuit. Then by applying KVL of the input circuit, see here, so we'll get an here VG minus VGS minus Vs we have. There are the three circuits which are coming over here, sir, because here's the voltage Vs will be coming in the picture over here. So these are three types of voltages which are analyzed in the input of the circuit by applying the KVL here. So this will be equal to 0. Finally we will get the input voltage VGS will be equal to VG minus Vs. I have told that as Vs will be equal to the product of Is into Rs. So it's the equation which is resulted by applying KVL to the input of the circuit. Next, from the output of the circuit, by just applying the KVL to the output of the circuit, see here VDD will be equal to, the current is ID and RD. VDD will be equal to IDRD plus VDS plus Vs. So VDD will be equal to sum of all the sources present in the output of the circuit. The same I have drawn written over here. So VDD will be equal to sum of IDRD plus VDS, the voltage between the drain and source, and the voltage across the source resistance. So now this VDS, as we want the output voltage VDS, so VDS will be equal to VDD minus, taking this minus RD, and Vs can be replaced once again as an Vs is equal to Is Rs. The same I have replaced here. Vs will be equal to Is into Rs. But taking the next step by taking ID as common here, so the RD plus Rs. So this is the final value of an output voltage, and we know that the final value of output drain current ID is equal to IDSS into 1 minus VGS by VP whole square. It's on the same operating point we are using for this case, so that the Q point which is finally resulted as for the case of voltage variable bias, so IDQ is equal to IDSS into 1 minus VGS by VP whole square. The same, just the VDSQ is equal to same VDD minus IDQ into RD plus Rs. So only the terms, the source resistance have come into existence extra compared to the earlier type of technique. So similar fashion we can analyze the circuit by the self bias. Yes, I will see the last type of technique, that's a self bias technique to analyze the operating point Q, in this case of field effect transistors. So coming to the self bias circuit, see now here we have no voltage given as we have considered in the fixed bias, and there is no two resistances, there is no voltage variable. So it has been given only the gate resistance which is connected over here. The remaining all the circuit is similar as that of the voltage variable bias, except that it has been considered as a gate resistance, single resistance at the input of the circuit. And the simplified form of this circuit, it has been given over here, so it is entirely short circuited here. So as Ig will be of very small, so it has been neglected, as you can consider as a short circuit. It has been given at the input of the circuit, and we have a VGS voltage. It's an input voltage which is measured between the gate and source. Once again it has been given, and rest of the circuit output it has given the same. It is a source voltage measured across Rs, and once again the VDS voltage between the drain and source. Everything is same here. Now see, first now we'll see to the DC analysis. From the DC analysis, as we have seen this, whatever be the current ID flows in the circuit during the working principle of the field effect transistor, the same current will be flowing through the source terminal. Hence ID will be equal to Is. So that ID is given equal to Is, as there is no voltage source as this applied here Vg, then it will be equal to 0 here. And as Vs equal to Is into Rs, so we can write it as an ID Rs, as Is is equal to ID, so this can be written as Vs will be equal to Is Rs or ID Rs. Okay. Now from this, applying KVL to the input of the circuit, we can once again analyze as VGS equal to, so Vg minus Vs, as Vg will be equal to 0 as we have seen earlier. So replacing that, then VGS will be only due to the source resistance minus Vs. So Vs is nothing but once again the IDRs, so minus IDRs, which is equal to same, it has been given the value of VGS by applying KVL to the input of the circuit. Now we know that there is standard equation for the drain current, ID will be equal to IDSS into 1 minus VGS by VP whole square. Now, as from the earlier equation, as we have got applying KVL to the input of the circuit, we have got VGS equal to minus IDRS. Just substitute the value of this VGS with the help of the minus IDRS. Just replacing in this equation, we will get the resultant equation, that is IDSS into 1 plus IDRS by VP whole square. It is a final operating point output current ID, same we can consider as an IDQ here. And now by applying KVL to the output of the circuit, same VDD will be equal to IDRD plus VDS plus VS. So the sum of all these sources which are at the output of the circuit. By simplifying this, VDS will be once again will be equal to VDD minus ID into RS plus RD. So if you could observe, so whatever the value of output voltage VDS you have obtained in case of self bias, it is similar to the output voltage which is obtained in the earlier case voltage variable bias. Only it's in a drain current is different. So IDQ and VDSQ are the two operating point for the case of self bias. By this we have finished the all type of techniques of an operating point of a fixed bias, self bias and voltage variable bias of a field effect transistors. As we already know that the bipolar junction transistors are called as current control devices, and whereas field effect transistors are called as voltage variable devices. In a similar fashion, one of that, this FET is also called as a voltage variable resistor. So that can be explained by making use of the characteristics, the drain characteristics of field effect transistors, where it has been taken from the output current and output voltage. So here the output current, it is an ID, and the output voltage VDS, by maintaining the input voltage constant for different values of constant input voltages. So these characteristics have been plotted here. So you can see, you can observe here in case of the region before the pinch of voltage. So it is in a region before the pinch of voltage. The characteristics are varying linearly. So whenever the FET is operating in this region, so it is, we can call it as a voltage controlled resistor, and it has these curves represents the pinch of region. Okay, now as we seen that it's a field effect transistors are voltage control devices. In most of the applications, these field effect transistors can be used whenever it is varying in linearly. So these linear applications will be much more used in case of field effect transistors. At the instant when the field effect transistor is varying linearly, at that particular instant it will be used in most of the applications. So this usefulness of the field effect transistor when it is used in a linear applications, so that these can be called as a voltage variable resistors. So we can call it, and finally we can give an statement that, so whenever the field effect transistors are used in various linear applications, so that it can be called as a voltage variable resistor. See, now we'll see the comparison between bipolar junction transistors and field effect transistors, and how many parameters they are differing. So first, coming to the first parameters, control element. So how can these can be controlled? How can the output characteristics of this bipolar junction controlled, and how can be the field effect transistors output can be controlled? So the control element here, it's just now I have told that BJTs are current controlled devices, where the output current can be controlled by input current, so that it is called a current controlled devices. And whereas field effect transistors is a voltage controlled devices, as the output characteristics can be varied by varying the input voltages, so that it is called as a voltage controlled devices. These are the control elements for the case of BJTs and field effect transistors. Next, coming to the device type. So second parameter, this device type, so it is called a bipolar junction transistor. So it has so the polarity here, the device, it is called a bipolar. The device type, it is a bipolar because the conductivity is due to both type of charge carriers, the electrons and holes in case of bipolar junction transistor. So that it is the type of device is a bipolar device. Whereas coming to the field effect transistors, the current conductivity is due to only one type of charge carriers. It may be either due to the holes or due to the electrons. So that is a unipolar. Field effect transistors are called unipolar devices. So coming to the third parameter, types. So how many types of these BJTs and FETs are generally occur? So as we know that in case of BJTs, we have two types as NPN and PNP. So these are the two types of the types occurred in case of bipolar junction transistors. Similarly, in case of field effect transistor also, there are two types of these FETs. So it is named as N channel and P channel. So these are the different types occurred in case of BJTs and FETs. Next, coming to the symbols of these NPN and PNP. So the symbols of NPN and PNP, as we know that, see, always for case of NPN, so it is NPN, always current flows from P to the N terminal. So it is the symbol of this. So arrow mark, always the current conduction is from P to N type. So that this whatever be the terminal, it has been indicated by the arrow mark, it is called as an emitter, it's an a base, and it's an a collector. It's a symbolic representation of NPN. Similarly, for PNP, always. Now for PNP, you can see the same concept. The current flows from P to N over here. So arrow mark is represented like this. So whatever be the terminal, it is represented by arrow mark. Always it is an emitter, then it is an a base, and it is an a collector. So these are the symbolic representation of NPN and PNP transistors of an a BJT. Similarly, coming to the field effect transistors, the symbolic representation of N channel. So where it has even the three terminals. It is a drain, it's a gate, and source. So these are the three terminals. And for N channel, always, so the arrow mark is indicated towards the symbol. So this gives an N channel FET, field effect transistor, JFET. Or now coming to the P channel, it represents, it has three terminals as a drain, it's a gate, and source. Now the arrow mark is outward the symbol. Whatever be the symbol we have, the arrow mark is outwards towards the gate. So this represents the P channel, and towards the symbol it is an N channel. So these are the symbolic representation of BJT and FETs. Next, coming to the parameters. So as I have said that coming to the configurations, the bipolar junction transistors have three types of configurations. This as three terminals it has. The three terminals can be made common in one of the cases, so that it rises to three types of configurations. That is, we have a common base, common emitter, and common collector. And similarly, in case of field effect transistors, there are three types of configurations possible. That is the common gate, common drain, and common source. So these are the configurations of these two devices. Next, coming to the input resistance. So the input resistance, as I know that the bipolar junction transistors, it has two junctions. One is an emitter junction and other the collector junction. This emitter junction is at the input, which is always forward biased. So because of its forward bias, it has low resistance at the input. So that it is having a low input resistance. Always the input of the circuit is forward bias, emitter junction is forward bias. So whatever be the circuit, it is forward bias, obviously the resistance will be less, so that it is having a low input resistance. Next, coming to the field effect transistors. While coming to the field effect transistors, always the input circuit will be of reverse biased. So because of which it has a high value of resistance, so that it is having high input impedance. So the input resistance of the field effect transistor is high for the case of FET and low for the case of BJT. Next, coming to the another parameter, sensitivity. So it is the sensitivity of the bipolar junction transistor is high. Okay, and whereas for the field effect transistor is low. Means if there is any variation in the input side, so it is very high sensitive. It's very delicate. The output characteristics will be varying for small variation in the input voltages or input parameters. Whereas it doesn't vary, the variation of the output will be of much less even though if we vary in input parameters. So that the sensitivity will be high for the BJT and low for the FET. Next, we have a relation between input and output characteristics. So what will be the relation between input and output characteristics for BJT? As we have said, then it is in a linearly variation. The input and output characteristics for the case of BJT will be often a linear, and whereas coming to the FET, it is in a non-linear. So next parameter, we have a thermal noise. The thermal noise it is nothing but, as we have said, that the bipolar junction transistor, it is called where the bipolar, the conductivity is due to both type of charge carriers, electrons and holes. Due to this, whenever these charge carriers will try to move towards the junctions, the noise created in the device will be high, so that the thermal noise produced in case of bipolar junction transistors will be high, as the conductivity is due to both type of charge carriers. And whereas coming to the field effect transistors, where the conductivity is due to only one type of charge carriers, so the noise produced within the device during the operation will be of less, so that the thermal noise will be low for the case of field effect transistors. Next, the last parameter, gain bandwidth product. So the gain bandwidth product, it's a high for the case of bipolar junction transistors and it's low for field effect transistors. It's one of the greater disadvantage compared to the BJT and FET. So all other having a good advantages, whereas the gain bandwidth product will be having high for the case of BJT compared to the FET. It's a greater disadvantage of FETs over BJTs. Next we will see the last topic of this unit, the uni-junction transistors. From the name itself we can say that it has a single junction, so that it has been given the name uni-junction transistors. So before going in details regarding this device, so you will see what are the topics, subtopics we are going to discuss regarding the uni-junction transistors. First we will see about the construction of this device, UJT. It can also be abbreviated as UJT. So UJT, uni-junction transistor. So first we will see about the construction of the device. Second we will see about the symbol, how it will be represented. Next we will see about the equivalent circuit of the device, how it can be represented. Next we will see about the one of the parameter we have, that is intrinsic standoff ratio. It is represented by eta. Okay, and we have the fifth one, principle of operation, how it will be operated. Next we will see the characteristics. Then finally the applications. So these are the topics we are going to discuss in detail regarding the uni-junction transistor. Now first we will see about the construction, how it will be constructed. So first consider a lightly doped n-type silicon bar. It has been considered over here. So where it is the conductivity will be less, as it has been lightly doped. Where it has been doped with at the center, at means nearer to the one type of the terminal, it has been doped with heavily p-type semiconductor into it, where a p-n junction is formed over here. So one lead which is taken from this p-type bar, which has been given the name as an emitter terminal, and the bar it has been given in one side with another terminal, it is an a B2 and it's an a B1, it's another terminal. So totally it is in a 3-terminal device, where the 2 terminals have been taken from the n-type silicon bar, given the name base 1 and base 2, and the PN junction, the terminal whatever it has been taken, so that is called an emitter terminal. So it is a 3-terminal device within a single junction, hence the name given as a uni-junction transistor. Next, coming to this symbol of this, so the symbol it has been given as the same, the terminal whatever it is been B1, it is also a B1. So the B2 it has been given as a B2, and at the input side it is called an emitter terminal, where the arrow mark is given towards it, it shows the direction of conductivity. So the conduction of the device will be in this direction, hence the arrow mark is given in this direction. So this gives the symbolic representation of uni-junction transistor. Next, coming to the equivalent circuit, which can be obtained from the construction of the uni-junction transistor. As I said, So where a single PN junction it has, so because of this PN junction it is represented by a normal diode. So where it has been indicated here, so between this, say it's in a PN junction which is given from the construction over here, so it has been given a normal diode, and the voltage drop across it is being represented by VD, and it's an emitter terminal. Now see, as this emitter terminal is taken nearer to the B2 terminal, so it is having the resistance will be less. The resistance of B2 terminal at this case will be of less and compared to the resistance towards the B1 terminal, because the gap provided between the emitter terminal and B1 will be more, and the gap here it will be of less. So because of this, the resistance here it will be of less than compared to the resistance across the emitter and B1. So there are two resistances possible in the construction. Same it is being indicated in the equivalent circuit diagram by RB2 and RB1. So this gives the equivalent circuit diagram for the construction of uni-junction transistor. We will see the next one of the parameter we are going to see now, that is an intrinsic standoff ratio represented by eta. So we can explain this eta with the help of the equivalent circuit just now we have discussed. So that is the equivalent circuit where it has two resistances. The drop across the voltage it is an VD. Now the voltage across the emitter it has been given as a VE, and the total resistance it is now it is RB1 and RB2 connected to, sorry, it's an RB1, it's an RB2 which is connected to the B2 and B1 terminals. Then the voltage which is obtained between these two terminals it has been given as VBB. Now the total RBB gives as these two resistances here, RB1 and RB2, the total resistance will be equal to sum of these two resistances when IE equal to 0. IE equal to 0 in the sense that when the diode is not conducting, there is no chance for the flow of current here. We can see here we are explaining the intrinsic standoff ratio under the condition when the diode is not conducting. So when the diode is not conducting, obviously the emitter current across the diode IE will be equal to 0. Under IE will be equal to 0, this total resistance will be equal to sum of these two resistances. Now we'll see how can we see what is the value of this intrinsic standoff ratio. So the value across this can be obtained as the VE equal to 0. The voltage drop which is obtained across the resistance RB1 can be given as here VRB1. The voltage drop across the RB1 resistance it is equal to, this can be obtained by voltage dividing rule, as VRB1 is equal to voltage drop we are going to calculate across RB1 resistance by total resistance into the voltage between these two resistances is VBB. So this can be written as VRB1. So this is nothing but intrinsic standoff ratio followed by this VBB under the condition when IE equal to 0. So as now the intrinsic impedance is the ratio of these resistances RB1 to the total resistance, which can also be further represented as RB1 by RBB under the condition IE equal to 0. So this is how we can derive the small equation of intrinsic standoff ratio, that is an eta, which is the ratio of input resistance, that is RB1 to the total resistance. Next we will see the principle of operation, how it can be operated. So as we have seen, there are two types of resistances possible here, RB2, RB1 within the device, as this obviously this first PN junction which is nearer to the RB2, so that the resistances will be less over here, and whereas it will be of high large, the distance will be more for the case of B1 terminal and PN junction here, so that RB1 will be of less higher value here. So these are the two internal resistances which are given here, represented by a single PN junction device where the terminals has been taken from B2 and B1. Here the voltage which is applied at the input is an emitter voltage, and the voltage across those two terminals B1 and B2 it has been given as VBB. So it's the construction of this as we have seen of an UJT. Now we'll see the operation. So there are generally two cases possible to know the operation of this uni-junction transistor. So now VA is in a voltage drop which is provided between the terminal B1 and up to the PN junction where it lies over here. Just we'll see what is the actual that VA here. Now first case, So VE and VA. Suppose the first case VE is an emitter voltage. It's a voltage across the terminal B1 to the junction. Now first case, so it's I have told that it's in a PN junction diode. So when the PN junction diode, it has the input voltage to this diode is VE and output voltage to this is VA. Suppose if it is in a PN junction, the input voltage is less than that of the VA voltage. Obviously it is in a reverse bias. So when it is operating in the reverse bias, the diode will not be conducting. Then we can say that UJT is in off state. So as VE is less than that of the VA, so this PN junction will be acting like in a reverse bias condition, so it will not be conducting. As this diode is not conducting, we can say that UJT is in off state. It is in a first state which is obtained for the first case. As VE is less than VA, the diode will be reverse biased, so diode will not be conducting and UJT is said to be in off state. So next we will see in the second case. So when this second case, as we are slowly increasing this VE voltage, as the VE is slowly increased, the input voltage is slowly increasing than VA. So it will be, was at one state it both will be equal, then after that VE we are still raising the value of VE. Then this input voltage will be high then compared to the output voltage, so that the diode will be now the forward state. So as the diode will be in the forward state, then diode automatically conducts. Then UJT starts conducting. Then we can say that UJT is in on state as long as VE is maintained more than that of the VA. Now we'll see what is that VA. See here, the total voltage VP is it is given by the sum of the VA plus VD. As we have seen, VA is the voltage across the junction and the terminal B1, and VD is the voltage drop across the diode. If VP will be equal to sum of these two voltages. So now this VA, just now have seen that we have seen VA is equal to eta into VBB, and this plus VD is the drop in voltage. So this voltage drop across the diode will be different. It depends upon the type of semiconductor device it has been used. As we know that for the case of silicon, so we have for silicon semiconductor it will be different, and germanium it will be different. The cut-in voltages, it has some standard cut-in voltages. For the case of silicon, so the cut-in voltage is of 0.7 volts, and whereas for germanium it is of 0.3 volts. So that this voltage drop VD across the voltage, it varies between the values of 0.3 volts to 0.7 volts, so which gives the total VP voltage, so that it will be equal to a sum of intrinsic impedance into VPB plus VD. So this is how we can maintain the UJT is in on state and off state based upon the input voltages given to the device. So this is how we can operate the UJTs in on state and off state. Now we'll see the characteristics of these uni-junction transistors. So how can we plot these characteristics here? So generally we have taken the voltage, it's in a VE and IE. So it's an input, we will see at the input case. So as we concentrate on the input case of the device, so we can plot the characteristics here, so that we can maintain just by varying the value of emitter voltage, input voltage, we can turn off the device and turn on the device. As we have seen the previous case, for the case 1, as long as VE is less than the voltage of VA, it will be of a reverse bias as it is in a off state. And second case, as long as this VE is slowly just we are increasing, then the diode automatically turn on. So this is how we can switching it off. Just we can switch on and switch on of the device just by varying the voltage of emitter voltage at the input side. Now coming to this the characteristics. So it's a VE voltage which is measured across the y-axis, and IE is a current which is measured across the x-axis. It will be in terms of milliamps. Now as we have seen that, so these total characteristics have been divided into 3 different regions. So one is called a cutoff region up to this stage, and between this it is called a negative resistance region, as the voltage is decreasing even though if we increasing the voltage. Hence we can call it as a negative resistance region, and third one is the saturation region. Now we'll see one by one how can we explain this cutoff region, how can this UJT will be shifting from one region to other region during the operation. Now first initially as VE, so this VE is less than the VA, so the diode will be automatically off, so as because it is not conducting, the voltage required to conduct is not just sufficient as we have given this VE. The first case as VE is less than VA, the diode is in off state. So now the diode, whatever be the current flows in the diode will be only due to the minority carriers, means a small current flows due to the minority carriers within the device as VE is less than VA. So that microamps of current which is flowing here, it is represented over here. So a small amount of current which is flowing in terms of microamps during the reverse bias of the diode. So this condition will be maintained as long as it reaches to the up to the point VP. It is called a peak voltage. Up to the point of peak voltage, the reverse current will be flowing through the device, that is in terms of microamps. So up to that region we can call it as a cutoff region, as this UJT is in off state. Next, suppose now we are slowly increasing the input voltage. Now as we are increasing the input voltage, then slowly this VE will be gradually going greater than that of the VP voltage. Then diode starts conducting as it is in a forward bias. So as when a small voltage is just enough to turn on the diode. If the diode is conducting, automatically the UJT is said to be in on state. So as it is in a forward bias, then the conduction in the device will start. Then we can say that UJT is in on state. So just a small voltage when it gives, that is in a VE, it is applied, then we are not applying that VE voltage. Once VE is increased over here, then the diode starts conducting, then a large amount of current, see here it will be flowing through the device. Now the voltage is just, it is falling down, because once if it is turned on, then it is not required for the voltage to increase the further conduction. So a small voltage it will turn on the diode, then the current through the device will be flowing due to the majority carriers, then the voltage it is not required here, so that it is just falling down here. The voltage is falling down from VP to the towards, it is called a valley point. Up to this point the voltage is continuously decreasing, whereas this current is increasing here. So this inverse relation gives is called a negative resistance region. As current increases, voltage is falling down. So this can be explained within a negative resistance region. So this state will be continued after the valley current. IV represents the valley current and VV represents the valley voltage. IP represents the peak current and VP represents the peak voltage. Once the current it crosses the IV, then slowly once again the voltage increases, it enters into the saturation region, then it works as a normal diode. Then the voltage drop will not fall further. When it crosses the valley current, the current increases, then simultaneously voltage increases. Then we can say that whenever the device falls in the saturation region, it will be acting like a normal diode. So this is how the UJT will shift from one region to other region by varying the input voltage VE. So this shows the entire characteristics of UJT. Next we have the last, finally it has been applications. So because of this negative resistance region, it will be used in most of the applications. The first we have seen that the UJT can be maintained on and off state, so that it will be used for triggering many of the other devices like SCR. So we can trigger this SCR by making use of this UJTs. So one of the application, and second one, it is used in the sawtooth waveform generators. Next, the third one, the most important application of this UJT, it is used as a relaxation oscillator. So it's an important application of the UJT as it is used as a relaxation oscillator. Thus we will see, thus we have finished all this unit. Just we'll see what are the topics we have discussed regarding this FET amplifiers. First we have discussed the for the case of FET amplifiers, it has been given as a there are three types of configurations which are possible. That is in a common source, common drain and common gate. So first we have studied about the common source, in which the three biasing techniques we have been discussed. That is in a fixed biasing technique. Then we have a self biasing technique. Then third one we have voltage variable. So these are the three types of techniques we have seen in case of common source. Then followed by the next type of a configuration, that is in a common drain. So for the common drain, so we have studied in a common type of an explanation. It is belong to all of these configurations, as we have a single type of common drain. It has been explained, and followed by any parameters we have been derived: input impedance, output impedance, gain we have, it is derived. Next, coming to the another topic, as we have seen after the common source, common drain, we have seen the generalized field effect transistors. In case of generalized field effect transistor, the three different sources will be connected in series with the three terminals of the field effect transistors. So later on we have seen about the field effect transistor as an, then we have seen the biasing. So biasing of field effect transistors, in which we have seen three different techniques even in this case. There is a fixed bias, then self bias, then we have a voltage variable bias. So these are the three different types of techniques we have seen in case of biasing of FET. Then last followed by a FET as voltage variable resistor. Then finally the comparison BJT and FET. The last we have seen about the UJT. So these are the topics we have seen regarding the field effect transistors, amplifiers. So in a simple topic which we have been discussed, it's a very small unit, and we can easily prepare for the external examinations.